So I have a YouTube account. Should be recording now. All right.
What's your YouTube handle?
It's basically just my name. If you search my name, it should come up. It should be my YouTube account. Is going to just be under my. It's my same as my personal Google account, so it should come up as. That's what my YouTube should come up as. If you do a search for Mr.Dowell on YouTube, I'm the only person who's going to come up. There's just not that many Dowells out there.
Are you YouTube famous right now?
No. And nor do I intend to be. These are obviously educational lectures. They ain't going to make me famous, nor would I really want to be YouTube famous. Okay. But I found last year, when doing these for a student, that they ended up being really helpful for everybody, so I figured we'll just continue it on. Okay? They'll be posted here. Also, too, class notes from now on will also be posted Canvas, okay, in a module or a announcement. I think I'm going to do it via a module as a PDF. So if you click in there, anything we do on the board will come up there. So you got this board, you got the video. You can reteach yourself this stuff back in your own rooms when you want to. All right. That being said, turn it off. Come on. Okay, we got to do this later. Okay, because we actually have to do stuff. All right. So today marks our. So what we're going to do today is we're going to actually start actual calculus. Okay, and the very first thing we're going to start with actual calculus is this concept known as the limit. Okay. We saw limits at the tail end of last year. Okay, if you were in my pre-cal classes, if you were in the honors pre-cal class, you should have also seen limits by this point as well. Okay, the limit ends up being pretty much the tool we use for everything we do with calculus ends up being this limit. Okay, what a limit is specifically is to kind of put it in layman's terms, a limit is the behavior a function has as it gets near an x value. Okay, to kind of put, or as it gets near a certain value. I shouldn't say necessarily an x value, but you get the idea. It's behavior the function is taking on. Probably the hardest concept to understand with the limit is when you're taking the limit of something, you're not figuring out what's happening at the point. You're figuring out what's happening around the point. Okay, essentially, you're saying in this neighborhood around x, or in this neighborhood around t, or whatever variable you're using, what is my function doing? Okay, and that ends up being the basic concept of a limit. Any questions there so far? Okay, now. I would love to go into great detail about the theory behind limits. Unfortunately, we just don't have the time. So instead, what we're going to do, we're going to start talking about is basically the ways to calculate a limit and kind of the nuts and bolts of what limits lead to. Okay? So we're going to start off basically calculating limits. And I'll introduce, as I go through here, and we look at some calculations, I'll introduce the proper notation you use and things like that. Okay? First thing we're going to do, okay, is look at limits numerically. Okay? Actually, take that back. We're going to do it graphically first. Yes, graphically first. Okay. Well, graphically, numerically, then algebraically, yes. All right. So, graphically, what we're going to do is we're going to look at the picture, and from the picture kind of gauge what the behavior of the function is around a certain point. Okay? So, what you'll often see done this way is you might get a question like the following. What is, okay, the limit of f of x at, and they'll give you a point. So we'll say at point A, okay? And what they're talking about here is they'll have a graphed function, okay, okay, like so. Let's make that look like an x. Okay, this is a function f of x we're looking at here, and it's worming its way around. We'll have it like that. There'll be some point on the x-axis a, okay, and what we're asking for is essentially what the behavior is around this point here, be a, f of a, okay? So, what the limit is asking for is not necessarily what the function is evaluated at a, it instead is saying, okay, when I'm close to a, when I'm in the neighborhood around a, what's my function doing? And as you can see here, the neighborhood around a, and I'm using this in a very general sense, the neighborhood could be as big or as small as you want it to be, okay? Typically, obviously, you get more information the smaller you make your neighborhood. If I make the neighborhood too big, then my answer for what my limit would be will just be kind of, it gets a little ridiculous after a while, okay? So when I get sufficiently close to a here, what's my function getting closer and closer to? F of a, right? So as we approach a in either direction, okay, the function gets close to f of a, right, in either direction. So in this case, we would actually say that the limit, and the symbol for what we use for limit is lim, as x approaches a, okay, of f of x, in my particular case here, would be f of a, okay? We're just saying, hey, what neighborhood am I going to, okay? Any questions so far? I'll give you a second to copy that down. Now, one thing I want to point out here that's very important to limits. Look at my arrows. Okay, I have some coming from beneath A, so coming from the left, approaching the point, approaching wherever A goes to, and I have stuff coming from the right, approaching whatever A goes to. Okay, limits are very much directional based. Okay, when you're calculating a limit, okay, the left side and the right side have to, for the limit to exist, they have to give you the same answer. Okay, now I could come through and I could give a separate problem, and we'll look at this later, of saying, okay, what happens when the limit comes from the left only? Or what happens when the limit comes from the right only? I could always do that. But for the limit to exist, both the left and the right have to agree. So this limit here is definitely f of a. Because, one, the function is not doing anything weird, is it? It's just a regular old line kind of doing its own, it's weird looking, but it's just snaking along. It's continuous throughout its entire domain by the looks of it. Okay? So, when that happens, as far as the limit is concerned, it's fairly easy to calculate. Okay? But these things can get more complex. There could be a jump here. The graph could be doing something really weird, like going up and down, up and down, up and down really quickly at a certain point. It could be doing lots of things like that. And so, when that's the case, obviously the limit gets affected. It becomes difficult to tell what's going on here. Okay? But so far, this is what we've got here. Any questions about graphically? Alright, let's take a look at a few graphical examples before we move on to doing calculating limits numerically. Alright, so let's look at one example here. Let's do an easy example of limits here. We'll do f of x equals x squared, and we want the limit as x approaches 2 of f of x. Okay? Well, doing it graphically, fairly straightforward. We'll just graph f of x equals x squared. What does that one look like? It's a parabola, right? Goes up like that, up like that. If I was being fancy, which I should be, I'll put in points here. We'll put in point 0, 0. Not drawing the scale, this will be the point 1, 1, 2, 4, and 3, 9. Again, Graph not to scale, just getting a general idea of what it's doing here. Okay? We want the limit as x approaches 2. So what's that going to mean here on my graph? Where am I getting close to? 4. Basically, where x is 2, going to be right here. Here's where x is equal to 2. F of x is going to be 4 in that case. And my limit is just going to say, okay, as I get close to 2, what do I get close to? Pretty obvious. It's just 4, right? Well, you're going to find that 90% of the time we take a limit, okay? This is exactly what we end up with. It just gives us the answer, it just gives us whatever f of x is. And that's because most of the functions we deal with are going to be polynomials, and the limit of a polynomial is just whatever the function is defined as at that location. They don't do anything weird, okay? So it's those times where we do get a weird function that matters, okay? In this case right here, though, everything's A-okay. No problems, all right? Everyone see how this one was done graphically?
So the answer would be 4.
Answer would be 4, okay? Because the left approaches 4 and the right approaches 4, okay? Let's take a look at another example, okay? One that isn't so clear-cut, or one that doesn't work so nicely, okay? Let us do... we'll do a rational function. We'll do f of x is equal to 1 over x minus 2, okay? And we want the limit as x approaches 2 of f of x, okay? Well, let's go ahead and graph 1 over x minus 2. What do we know about 1 over x minus 2? It's a, what type of function?
Rational.
Rational. And it's got an asymptote where?
At 2.
At 2. So we'll come over to 2. We'll put down our vertical asymptote there. It's got a horizontal asymptote at y equals 0. There's nothing added on the outside, so it's the horizontal asymptotes y equals 0 right there. Those are my asymptotes. Okay. And the graph itself then is just going to it's going to curve like that down this way and do something like this up this way. Don't really care that much about getting the picture exactly 100% correct. Because what instead we're just looking at is behavior as we get close to 2. Now, looking at this thing, 2 is an asymptote, right? Nicely marked for us already. So I don't necessarily need to put in other points, I just need to see what's going on as I get close to 2. What's happening to the left as I get closer and closer and closer to 2?
Negative infinity.
It goes to negative infinity, right? It goes down, negatively to infinity. How about from the right?
Positive infinity.
Goes to positive infinity. Okay. Is positive and negative infinity the same thing?
No.
No. They're at 2 different completely places, right? So because of that, there's no limit here at 2. I get 2 different answers, basically, as I approach from either direction. It'd be like if I told Tommy, come to my house from the east, and told Mac, come to my house from the west, and Tommy ended up at my house, but Mac ended up in Washington, D.C. Okay? 2 completely different locations, that shouldn't be, right? You want to come to the same location. Well, that's exactly what's happening here, okay? So when that happens, we would say there is no limit. Now, one thing you want to make sure you don't do here, limits are, oops, that's not what I want to do. Where is it? Right there. Go right there. Okay. I'm going to rewrite the limit equation here. One thing we want to note when we talk about the answer here is a lot of people, when you don't get an answer for something, they like to say, "Oh, it's undefined," or "Oh, it's not there." For a limit, okay, limits are never undefined. A limit either exists and gives you a number, or it does not exist. So the proper way to answer this question is the limit does not exist. Okay, and you can put DNE if you want to, but remember that whole notational thing. Don't start off by just writing DNE. Get used to saying limit does not exist. Okay, And if you want to, you can write DNE and say it means does not exist, and then next time you use it, just use DNE. Okay? But basically, the limit does not exist. Okay? That is the correct way to say this problem right here. All right, everyone got that? Okay. So graphically, we can see here, there's no limit because you've got this big jump. Okay? In our graph. Let's take a look at another one. We'll do one more of these before we start looking at them numerically. And this will actually get us into looking at things numerically. Okay? Let's look at the function f of x equals x squared minus 4 over x minus 2. Okay? And again, we want the limit as x approaches 2 of f of x. Okay? Now, this is kind of a weird looking function, right? What can we do to this function? We can factor the top, right? And kind of clean it up. What's it clean up to be?
X plus 2.
Just x plus 2, right? So, good. When I'm graphing it, I would graph this as just the line x plus 2. But at 2, what am I going to have? A hole. Okay? A place where the graph doesn't exist. So this would be the graph of f of x right here. Something that looks like this right here. Okay?
That would be the limit.
Now, what'd you say?
That would be the limit.
Ah, okay. So, would the limit exist at the hole?
Yes.
It would. Why?
I can tell you. It becomes the value.
Well, think about things graphically.
Just like the value limit.
Because it's-
the rest of the value of the function.
Okay.
Something near it. It is approaching that.
It is approaching the hole, and as Khalid said, remember, the value of the limit is not the same exact thing as the value of the function. So both of you have got it right. Essentially, it's a combination of the two. Remember, limits don't have to equal their functions at their point. Okay? What they are instead is saying, where does the function go? What's it getting near to? And as we can see from the left here, we get near the hole, and this hole, by the way, is at the point 2, 4. And from the right, we get near the hole, right? Remember, limit don't care what happens at the hole exactly. Limit don't care. It just does what it wants. Okay? So, so instead what we want to do is we just want to say, okay, doesn't care what happens at the hole, it just says what's happening around the hole. And around the hole, we go to 4. So the answer to this then is that the limit as x approaches 2 of f of x is 4, because that's where we end up. That's the neighborhood we're in. Okay? So it'd be like as if, in this case here, it'd be like I told you, I gave you an address for my house. You get to the neighborhood, and where my house should be, there's an empty lot. Okay? Does that mean there's something wrong with the neighborhood?
Yes.
Well, you maybe, but there's nothing wrong with the addresses. The address is correct. It's just that when you got to that address, there was no house there. Okay? Maybe I live in a tent. Maybe that's where I park my RV. Who knows? Okay? But the idea there is the directions make sense. You end up in the right place. Okay? Tommy and Mac both meet each other, coming from the east and the west. It's just that there's no house there. Okay? That's what's going on here. But that's fine. You ended up in the same location both times. Okay? Any questions? Okay. This one, by the way, is great to show how limits work numerically. Okay? When we saw the limit numerically, what we're essentially doing is we're creating ourselves a chart, if you will, of points approaching the point we want in question. And we get nearer and nearer and nearer to it until we kind of get an idea of where we're pointing at. Yes?
If you just plug it into a calculator, then hit the what or chart and then it'll say error. Because it's technically a hole.
It's technically a hole, but remember the chart's telling you what the exact values are
So it'll say
at
error.
each location. But remember, we're not saying what's happening exactly at that point.
Oh,
That's not what it's talking about.
I'm not denying that it's a.
Oh, you're just saying, can we just can we use our calculator to calculate a chart real quickly?
Yeah, and just look for the error. If it's a hole.
If it's a hole, I'll tell you the hole there. Yes, you could do it if you're looking for holes, but two things. One, you may not always be allowed to use a calculator, which will happen. Remember, half the stuff we do in this class will be without the aid of a calculator. Okay. But also, two, it actually, what we're after with the chart you're about to see here in a second is not necessarily where the hole is or what's happening at that point. We just want to, again, know what's happening around the point. And that's what the chart's going to be telling us. Okay? So in calculating out a limit numerically, what we're going to do is we're going to look at values getting closer and closer to the point in question. Okay? From both directions. So I might come through here and say, okay, we'll look at the previous example. F of x is equal to x minus 4 over x minus 2. Okay? And we want to know the limit as x goes to 2 of this function. Okay? Well, instead of graphing it out, what I'm going to do is I'm going to create myself a little chart here. I'm not very good at drawing. Here's x. Here's f of x. And I'm going to pick points close to 2, okay, from both above and below. Okay? So, one point that's close to 2 from below would be what?
1.99.
So 1.9 or 1.99 or 1.999. You guys remember this from last year. That's good. Okay. And we'll take it to 3 decimal places. That's the industry standard, if you will, for what we're up to. Okay. So that's coming close to 2 from below. What should we do from so above? What should we choose? So again, things close to 2 from above. So like 2.1, 2.01. 2.001, okay? Alright, so there's our chart. Now we just need to know what the f of x values are. This is where a calculator can come in handy because it can just rattle off the answers really quickly for you. However, remember this function simplifies to be x plus 2. So 1.9 plus 2 is 3.9. 1.99 plus 2 is 3.99.
Does it come out to be x plus 2?
This thing? Yeah, that's what I'm saying.
How does it? I thought we
Oh,
It was squared.
oh, it's square at the top. My bad. I left that out. Sorry. There we go. Now it comes out to be x plus 2. Thank you for catching my mistake. Okay. And then when we do the same thing, okay, so from below, what do my values approach?
4.
They get closer and closer and closer to 4, right? Okay, and if I choose values getting closer and closer and closer to 2, those values are just going to get closer and closer and closer to 4. Okay, well, do the 2.00, do it on the other end too, and you'll notice they also get close to 4. 2.1 goes to 4.1. 2.01 goes to 4.01. 2.001 goes to 4.001. Every time I choose something getting closer and closer to 2, the answers get closer and closer to 4. So what does this chart numerically tell you that the answer should be? 4. Okay? Remember, the function is undefined at 4, but the limit doesn't care about that. The neighborhood you go to is still the neighborhood around 4, so that's the answer for my limit. Okay? Any questions there? Okay. This is how you would do one numerically. And how it would fail numerically would be if I did something like, if there's a problem with it numerically, obviously the left hand and the right hand sides won't line up. Okay? They'll go to different locations. Or maybe one location you can't even approach from to begin with. A classic example of that would be the square root function, whose domain just abruptly stops. Okay? Well, if I'm trying to figure out the limit at that point where it stops, it turns out it doesn't exist because there's no neighborhood. Okay? Neighborhood exists on one side but not the other. In fact, why don't we take a quick look at that because that's a good one. Okay? So we're still doing things numerically. Let's look at f of x equals the square root of x, and we'll do the limit as x goes to 0 of f of x. Okay? Alright, making my numerical chart. Okay? Things less than 0. So maybe negative 0.1, negative 0.01, negative 0.001. Then above 0 we'll do 0.001, 0.01, and 0.1. I gave myself a little extra box there, but whatever. Okay. What's the problem with these negative answers? They don't exist. You can't, remember, with real numbers, you can't take the square root of a negative number. So this would be basically error or undefined. For those three. And then from above, you can't get answers. And so you do actually have an answer for these three here. They get closer and closer and closer to 0. So that's what they get close to. I don't actually know the numbers off the top of my head, but we'll just say like near 0, near 0, near 0, okay? So what's the problem here though? From the right, I got an answer, right? It was near 0. But from the left, what happened? Undefined. So numerically, I can see the left-hand neighborhood doesn't match the right-hand neighborhood. Okay? It'd be like it'd be like telling somebody, approach my house from the west, and they came to my neighborhood. Tell somebody else, approach my house from the east, and every time they tried to, they would fall down like a bottomless pit, or they couldn't do so. Their car would break down or something. It would just be impossible to do. And that's the case here. This limit does not exist. Okay? And again, numerically, it's because from here it doesn't exist. Now, if I were to change this, by the way, if I didn't do it exactly at 0, but did it still for a point very close to 0, let's say like 0.001, and ask for a limit there, the limit would exist. Because I could have a left-hand side I can approach from in that case. Okay? It's just here at 0 that things break down. Okay? Any questions so far?
So it's like that for every single square root?
Not every single square root, but a lot of them have this behavior. And so you do have to, when finding a limit of a square root type function, that is something you'll have to test for. Okay? There are square root limits that don't do this. Okay?
Oh, so if you just don't use 0, if you use like 2, then it would have a limit.
Oh yeah, if I use 2 in this, yes, there would absolutely be a limit at 2 for this thing. It'd be square root of 2 would be the limit. It's just 0 is weird because that's where it goes from existing to not existing. And so there are other square root functions. Like if I put like a +1 in there, then the location would be at -1. That's where it would stop going from existing to not existing, that sort of thing. Okay, so kind of limits numerically do have a thing to you do have to consider. Okay. Any other questions about this so far? All right. Let's talk next about some interesting functions. Okay. Let's look at functions where there's some issues. A function can be defined everywhere, but not necessarily have a limit at a point. Okay? And simply because the neighborhood doesn't work out well. Okay? A classic example of that would be something like the step function. Okay? Where at the points where you do the step, everything from the left gives you one answer, but everything from the right gives you a different answer. So at the jump, there's no answer. We saw that with it's defined everywhere, but there's no limit because the answers don't match. Kind of like the same way with the irrational function we did earlier. When the answers didn't match, we couldn't get a solution. Okay. There are functions though that seemingly should have a limit at a point, but end up not because of just the way they work. A classic example of this is a very bizarre trigonometric function, the sine of 1 over x. Okay. And we want the limit as x approaches 0 of the sine of f of x here. Okay? Okay. Now, again, kind of obvious if I just jam 0 into this thing, I won't get an answer because it will be undefined in there, and that doesn't work. But limit doesn't care about what's happening actually at 0. It wants to know what's happening near 0. Okay? So what we're going to go ahead and do is we're going to make ourselves a little chart here and fill in values of x getting closer and closer and closer to 0. Okay? Oops. X and f of x. Okay? And the values we're going to pick are essentially, in this case, to make life easy for us, we're going to choose values of 2 over pi and make the denominator get smaller and smaller. The reason for that is because when we stick 2 over pi in this thing, what's this thing going to do? It will do the reciprocal, we'll get pi over 2, which we know the answer of easily, right? So, we'll do 2 over pi first. Sticking that into f of x gives us the answer of 1, right? No problem there, correct? Alright, next one we're going to do is let's do 2 over 3 pi. Is 2 over 3 pi greater than or less than 2 pi?
Great.
Less than.
Less than. We're making the denominator bigger so it gets smaller. It's getting closer to 0, right? What's this value come out to be, though? If I stick it in. Is it 1? If I stick it in this thing, it would become sine of 3 pi over 2, which is -1. Guys, learn your unit circle. You guys have to master that.
What?
Okay?
3 pi over 2 is not to less than 1.
3 pi over 2 on the unit circle.
I'm super rusty.
Okay? Here's where 3 pi over 2 is.
Yeah.
Its coordinates are 0, -1. Remember, the sine wants to know what y is. So the sine of 3 pi over 2 is saying, what's the y coordinate there? It's -1.
That's it.
Just like pi over 2 is up here, and that's 0, 1. Okay? So the next point I'm going to put in, okay, is going to be 2 over 5 pi. Okay? 2 over 5 pi, looking at our unit circle, there's basically starting here, there's pi over 2, 3 pi over 2, 5 pi over 2 is the same thing as pi over 2. So what's this value become? 1. If I did 2 over 7 pi, what do you think it's going to be? -1. So as this gets closer and closer to 0, what does this one get closer and closer to? It oscillates. It gets closer and closer to either 1 or -1. And the problem is it can't settle on either one, can it? Okay? And so because of that, the limit here does not exist. Okay? And if we look at this one graphically, we would see that to be the case. So I bring up the calculator. Wants to be slow this morning. There it goes. Okay. I'll make sure I'm in radians. I am. We'll do clear the sine of 1 over x. Okay. And we'll set my window. We'll keep it small. We'll go from -pi over 2. To pi over 2. So that should all be good right there. If we graphed it, here's my function that comes in. Comes back out again. As you can see, out far from 0, everything else all happy and nice, right?
Yeah.
But what happens as I get closer and closer to 0? It goes nuts. Okay? It goes crazy. It can't decide where it wants to be. Okay? And so such an oscillating function is defined everywhere, but there's no limit. Okay? Any questions about that so far? Okay? All right, good. All right, so in that case, I'll let you guys go ahead and get an early start walking downstairs. If you have any questions, again, about the review stuff, okay, come see me. Okay? The review quiz